Welcome class, and so we are at the fourth recording of this week, and in this recording I'll do some examples and problems related to the MOSFET amplifier theory that we studied in the last class. Okay, so we studied that there are first of all there's three defining properties of an amplifier, which is the input resistance, the voltage gains, and the output resistance. Similarly, there are three configurations: the common source, the common source with a source resistance, then the common gate, and the common drain or the source follower, right? So let's look at the examples. So I'm on slide 56 and I'm looking at an exercise 7.21. So unfortunately, in the 6th edition of the textbook, the one that we are actually following, there aren't many good examples that he has solved on these topics. On the other hand, I find that in the 7th edition, there's more material that I can pick from, to help you with the problems in this for this material. So when you see 721, it just means not the 7th chapter in our 6th edition, but it's the 7th chapter in the 7th edition of the textbook. This should not matter to you, because as long as you follow the material in the actual problem, that's more important than getting confused about the actual problem number or the exercise number. Okay, so we are talking about a CS amplifier here, a very basic question on CS amplifier. It uses a MOSFET biased at ID equals 0.25 milliamps, and the over voltage VOV is given to be 0.25, and the drain resistance is given to be 20 kilo ohms. The amplifier is fed with a signal source which has 100K resistance of its own, and there is a load or RL of 20K. So all the values necessary are given to plug into the formula and solve it. It should be pretty straightforward. We have to find Rin, RO, the open circuit voltage gain, then the voltage gain AV with the load, and then the overall voltage gain GV. Okay. Then there is a part B to this. If to maintain reasonable linearity, the peak of the input signal wave is limited to 10% of 2 OV, what is the peak of the sine wave voltage at the output? Okay. Alright, so let's see how to solve this. Exercise 721, here it is. So it's in this PDF file called week 4 amplifier part B class problems. I apologize, some of this got erased, but most of it should be pretty readable. So here's a CS amplifier given RO equals RD equals 20K. Well, RD is given and that's RO. AVO is this formula. GM can be found as 2ID by VOV. So GM is 2 into ID is given, so it's easy to find GM. Then you can find AVO using this formula, minus 40. RN is infinity. RL is 20K. AV, not AV0 or AVO, this is open circuit voltage. This is just AV with the RL included. So that formula, you just put, instead of RD, you put RD in parallel with RL. So that becomes minus 20 volts per volt. So GV equals AV in this case for a common source amplifier. GV and AV are the same. It's minus 20 volts, the same minus 20 volts. Actually, you should see that. Hold on, let me. Yeah, you'll notice that the AV and the GV are the same for a common source, right? That's why we did that. Okay. Lastly, VO equals GV into V signal, right? V signal is supposed to be, and this is for the second part of the problem, V signal has to be limited to 10% of 2OV, which is 0.1 times 2 into 0.25. So you want the V signal to be 0.05. So what will be the VO? It will be minus 1 because there's a 20 times amplification. Okay, pretty simple, but unless we do one or two of these problems, the ideas that we have studied and the formulas, you don't get practice in applying them. Okay, next we have a CG, common gate amplifier, right? Previously we had a CS, common source. Here it's a CG. Here we are required to match the amplifier with a signal source whose R signal is very low. R signal is 100 ohms. Remember, the CG is a great impedance matching amplifier, right? It can take the very low signal or very low input resistance, which is the source resistance, and match it to maybe the next stage, which could be a CS amplifier, right, with a high input impedance. So at what current ID should the MOSFET be biased if it is operated at an overdrive voltage of 0.2. So VOV is 0.2. If the total resistance in the drain circuit is 2 kilo ohms, what overall voltage gain is realized? So pretty simple. For a CG amplifier, our signal given to be 100 ohms, VOV is given to be 0.2. So Rn is 100, which is 1 by Gm. So Gm, the transconductance, is 0.01, right? Which is just 1 by 100. Also, Gm has another formula, 2ID by VOV. So from here, and knowing Gm is so much and VOV is given, you can find ID, the biasing current, as 1 milliamp. Given that GV, the overall voltage gain, is this formula, Rn by Rn plus signal times Gm times drain resistance, which is given to be 2K, right? Yeah. So if you multiply all that, you should get 10 volts per volt as the gain. Yeah, the total resistance in the drain circuit is 2 kilo ohms. Alright, then we move on to exercise 729, where we come up with a CD or source follower, common drain or source follower configuration. Now this is used as the output stage of a cascaded amplifier, right? So we saw the three benefits, the three uses for the three configurations. The CG, common gate, can be the input stage. Then we have maybe a number of common source stages to give us the actual amplification, and the output stage of the amplifier is a CD, common drain or source follower. It is required to provide an output resistance of 200 ohms, right? The output resistance is matching some kind of device, maybe a speaker or something, with a very low impedance of its own. So the output resistance is low. The MOSFET has these values, Kn, I think you know what this is, and is operated at an over voltage of 0.25. Find the required W by L ratio. Also specify the DC bias current ID. If the amplifier load resistance varies over the range 1K to 10K, what is the range of GV, the overall gain? Okay. So Cy, we are given Kn prime, which is here in this formula, and then for Gm you have another formula, and then for gain you have this formula. So basically we are going to apply these three formulas here for the CD amplifier. So given Kn prime is 0.4 milliamps per volt square, V over voltage, Rho output resistance, Gm is 1 by Rho, so that's 5 milliamps per volt. Gm is also this, so from this you can find W by L because everything else is given. Again, plugging in the W by L here, you can come up with ID. Okay. The second part of the question says if RL varies from 1K to 10K, GV varies from this to this, right? The formula is pretty simple, RL by RL plus RO. So it varies from 0.83 to 0.98 depending on the output load resistance. Okay. All right. So those were 3 examples of the numerical related to the 3 different amplifier configurations that we studied in the last lecture. These formulas, they are all in the textbook. Some of them are in this table also, right? So just make sure you know where to go looking for formulas to help you solve these problems. For example, we needed for the source follower, we needed the GV, right? So that's the equation, RL by RL plus 1 by GM, and 1 by GM is nothing but RO. So that's where I got this. Okay. All right. Let's move on to biasing. I'm skipping slides of theory 62. We come up with the first example from the textbook on this topic. Again, for some reason I find that in this chapter there are not too many examples that has been given in the textbook, at least in the 6th edition. So I had to go look for the 7th edition. But luckily we have one good example on biasing, particularly this resisting divider, voltage divider network example. So again, this is in the textbook. I shouldn't be spending too much time, but let me just walk you through it. So it is required to design this circuit to establish a DC current ID of 0.5 milliamps. So this current ID also flows from the drain through the source, right? Because this is 0, as you know. The MOSFET is specified to have a VT of 1 volt, and this quantity, I know it has a name, I forget, but that is given to be 1 milliamp per V square. Sometimes they'll skip this W by L, in which case this is just Kn prime is given without it, but in this case the whole product is given. For simplicity, neglect the channel width modulation, that is, assume lambda equals 0, that means RO will be 0, the small RO. Use a power supply VDD of 15 volts. Now luckily, he has also given you the circuit for this example with some numbers, so that makes it a little bit easier. Okay. So you can see the answers, like VG is shown here, VD is shown, VS is shown. But how to get these, obviously we'll look through it. Calculate the percentage change in the value of ID obtained when the MOSFET is replaced with another unit having the same Kn prime WL, but VT has changed. So the VT was 1 volt here, now the VT is 1.5 volt here. So we have to see with this, which is a 50% increase, right, from 1 to 1.5. So will our ID get also moved by 50%? We hope not, because this, we are told, is a very good and stable biasing network. So let's see what percentage change happens in ID. Okay. So here are some formulas to help you solve. When they say design, you're supposed to find all these values, right? The values shown here, 8 meg, 7 meg, and all this. How do you get them? You get them through these formulas. So for example, our drain, right? This 10K you get with this formula, RS you get with this formula, and so on, and ID, VGS, and so on. So let's see how to solve this problem. Well, it's actually solved in your textbook, so I don't want to spend too much time. I want you to go through it, and there really aren't too many tricks in this example. Everything seems pretty straightforward. Yeah, I will let you look through it, and you'll see, for example, the answer to this question, what is the percentage change in the current, bias current? It's only a 9% change. So even though the VT changed by 50%, the effect on the ID was not too big because we created this circuit. Okay. All right. So I will let you study that, and I advise you to totally understand the steps, because this is very fundamental, very important to understanding amplifiers in general. How to establish a good bias point using somewhat of a more complicated circuit. Okay. Okay. I'm going to move on. Problem 795. Same thing. Really is kind of a repeat of what we just did, but I wanted to give you a second example. So here we are given Vg as 5 volts at this point at the gate, and Rs is given 3 kilo ohms. The transistor has a Vt of 1, Kn is given. What bias current results? If a transistor for which Kn is 50% higher is used, what is the resulting percentage increase in ID? So similar to what we just saw, let me quickly go through it. All this data is given. ID equals this. Actually Kn is given, not Kn prime. So that's a mistake. I should take that out. ID is this formula. This is just the over voltage, right? You know that. So VGS is Vg minus IDRS. So if you know Vg, that Vg is the sum of, by KVL on this circuit, this Vg equals this VGS plus the drop in this resistor, right? Sorry. So VGS, to find VGS, we can do the reverse, which is Vg minus 3ID, sorry, minus IDRS. RS is given 3, ID we don't know. So ID is this from this formula. VGS we don't know, still it is in terms of ID. So we put that in terms of ID. So you have an equation which has ID in two places, but you can solve that to get a quadratic equation. So solving, you get two values. Only one of them is meaningful. How do you check? If you use one value, you can see that the transistor is cut off because VGS falls below VT. That's not allowed. With the other value, we get VGS is 2 volts. So VGS is greater than Vt, which is 1 volt, and also it's greater than the over voltage 2 volts. No, V over voltage is where did we find it? Is it given somewhere? No. Oh, it's not given. 2 volts. Okay, I guess I should have said greater than Vt, not VOV. Sorry. Yeah, VGS is greater than VT. Yeah. So choose the second value, right? This should be Vt. So we choose this value instead of the other one. Now if K1 changes to 3 milliamps, Kn, which is here we had 2, so that's also a 50% increase. What happens to the current? The current, you can plug it in, it's the same equation. Now instead of 2, we have 3 here. So ID has 2 values again, and the right answer is this 1.05, which means it's a 5% increase, right? Because previously we got 1 milliamps, now it's 1.05. So there was only a 5% increase in the bias current in the drain. So that's 795. I hope that was clear. Let's move on and find exercises 737 and 38 related to a CS amplifier. So this will be a complicated design exercise. First, 737, we just have to find these values of the resistors. Given a certain value of ID, Vs and Vd are also given, which is the voltage is here. So a lot of information has been given, so that makes it a bit easier. Vt is given, Kn is given, Va is given, ID is given. So more information than required, I guess. Find the values of Rs and Rd, which also means you have to find these values. Now if a current of 2 microamps is used in the voltage divider, right, in this if you have 2 microamps which goes from there to there, because nothing goes into the gate, specify the values of Rg1 and Rg2. Give the value of the MOSFET parameters Gm and Ro at the bias point. So lots of stuff to find. Then we have another problem, which also is an exercise problem, to find the input resistance, output resistance and overall voltage gain when a certain source with 100k resistance and a certain load with 20k resistance is connected to this circuit. Okay. So here are the formulas to use that you're going to find. So first of all, ID is this, so it helps you find VOV. Then we can find the VGS at the operating point, which is the gate to source voltage, so VT plus VOV. VG equals Vs plus VGS. For this part, you need Rin, which is the parallel combination of this. Then you can find Rin, Ro and overall voltage gain using these formulas. Okay. Alright, so let's look at this 737. all the data given I've written here. First, to find RS and RD. So RS is Vs by Id, you can find it pretty straightforwardly in this case. RD is also easy, it's VDD minus Id by Id, because this is just this voltage minus this by the current through it, right? I guess I didn't show that formula here, but you can see it. 15 minus 6 by 0.5, that's 18 K. Now to find Vg, the DC bias gate voltage. So Vg is Vs plus Vgs, you've seen this before. Vs is given, Vgs is Vt plus Vov, these are all given. Well, actually Vov is not given, but we calculate that using this because we know everything else. So Vov is 0.5, so you put 0.5, so you get Vg is 5 volts. So same current of 2 microamps flows in Rg1 and Rg2. So Rg1 equals VDD minus Vg by I, which is 5 meg. Rg2 is Vg minus Vg by I, Vg minus 0, because Rg2 is this. So if you know this and this portion is ground, you can calculate Rg as the Vg by the current in it, which we are told is 2 microamps, sorry, 0.5 microamps. Here, yeah, 2 microamps. So you get that. So it's 5 and 2.5 are the 2 meg, by the way, are the 2 bias voltage divider network resistor values. Lastly, we are asked to find GM, 2ID by VOV, RO, VA by VD, and that I think is it. Oh, then we have 738, which is the next problem. So here is 738. So Rn in this case is the parallel combination of this and this. RO is this by small RO, or RD in parallel with small RO. GV, this formula, you get minus 17. Okay? How do we get RO, right? That's the question. Let's see if I show you that. VA is given. Yeah, RO is VA by ID 200K. So that's what I put here. Okay. All right. So that does these two examples or exercises related to a common source, CS amplifier. Now, CS amplifier with a source resistance, right? So the same problem we just solved, this 737 and 38, is continuing. So here the goal is VGS is to be reduced to half its value. So the signal at this point, we want to reduce it to half its value, because that helps to keep the input signal small enough. The V signal can be the same, but this can be reduced by having this extra resistor, right? So what value of RS is required to achieve that? Then what happens to the amplifier gain? In this analysis, we are told you can neglect RO. Okay. So to solve this, we use this formula. VGS with a source resistor is this formula, and given this system configuration, we need to find GV. To find GV, you can either, well, you can use AV and plug it in here, or you can directly use this formula to find overall gain. Okay. So let's see how that's done. We found GM to be 2 milliamps per volt above. VGS is VI by 1 plus GMRS. The condition given is that VGS should be only half of VI. So VGS by VI, if you move this here, is half. So half equals 1 by 1 plus 2RS. Okay, you see what I've done here? Then you can solve for RS and you get that as 0.5 kilo ohms. Now mind you, we use the 2 milliamps directly here, right, in GM. Hence RS comes out to be in kilo ohms. So we have some of these shortcuts, they're used in the textbook, and I'm using the same shortcuts because you always seem to multiply milliamps and kilo ohms, so you don't have to show both of them because they cancel each other, right? But make sure you don't make those mistakes with relation to the mega, kilo, milli business. Alright, neglecting RO, you can write the equation for GV, the overall gain, as this times this. So I show you that it comes out to be minus 8.9 volts per volt for your common source amplifier with a source resistor. Okay. Alright, what do we have next here? Common gate. I don't know if I have an example of it. Oh, here we have a common source amplifier with a source resistance still, and I think I have the source follower next. Yeah, we only have 2 problems left. So let's focus on 7121 next. So what is the problem? The MOSFET has some values. What you'll notice is there's a plus 5 and there's a minus 5 at the bottom here. Okay. Open circuit, no load. Find the values of RS, RD and RG so that a certain ID is established. The largest possible value of RD is used while a maximum signal swing at the drain of plus or minus 0.8 volts is possible. So at the drain, which is here, VD, we want a maximum signal swing of plus or minus 0.8. And the input resistance at the gate is 10 meg. So at the gate, we need 10 meg input resistance. Neglect the early effect. Capacitance can be considered open for bias calculations. Find the value of GM and RO at the bias point. Now if terminal Z is grounded, if this is grounded, and terminal X is connected to a signal source having a resistance of 1 ohm, and terminal Y is connected to a load resistance, then find the voltage gain. So he's given us 3 different combinations actually, which really are the common source, the common gate and the common drain. He's just not calling that. First he gave us kind of a general circuit, and then he's acting cute and without naming them, he's giving us all these conditions. Similarly, if terminal Y is grounded in part D, if this gets grounded, then find the voltage gain from X from here. from X to Z with Z open circuitry. So Y is grounded, Z is open. What is the output resistance of the source follower? Then it becomes a source follower or a common drain circuit. Lastly, if terminal X is grounded, that means now it's a common gate. X is grounded, terminal Z is connected to a current source. So you have a current source here delivering a signal current of 50 microamps and having a resistance of 100K. Okay, so this is a current signal source. That's what I guess he should have said, but I'll add that. Not the bias voltage, it's a current signal source. Find the voltage signal that can be measured at Y. So that's the common gate connection we studied. The gate is grounded, the signal comes in on the source, and the output is taken out from the drain. So for such a connection, find the voltage signal that can be measured at Y, which means if you find the gain, overall gain, then you can find the output voltage. So interesting problem, many things there. So let's go ahead and solve them one piece at a time. 7.121 part A. Find the values of RS, RD and RG, which means find the bias conditions. Alright, maximum signal swing at drain is shown, plus or minus 0.8, plus the other stuff is shown. So based on this, we should be able to solve. Now Rin is Rg, which is also given to be 10 meg. Yeah, the input resistance at the gate is 10 meg, so that is Rg, which is also Rn. So ID, Rn in certain conditions, I guess, let's put it that way. Okay, so ID is given 0.4, ID has this formula, so we can find VOV to be 0.4 volts. Our source is V source minus the voltage. We are talking about the source part, right? So our source is this V source minus this divided by the current, right? So I use this formula. We know V source is minus 1.2 plus 5 divided by 0.4. How do we know this is minus 1.2? Here's the calculation. We start with Vg equals Vgs plus Vs. There's no voltage at the gate yet, so that's 0. So Vgs plus Vs equals 0. So Vs is nothing but minus Vgs, which is minus Vt plus VOV. Vt is given, VOV we just found, so we can get Vs. So you put that Vs, you get Rs equals 9.5 kilo ohms. So the transistor must remain in saturation, not go into cutoff. The minimum drain voltage must be limited to Vg minus Vt, which is 0 minus 0.8 or minus 0.8 volts. Now this Vg minus Vt is shown here, right? The limit of saturation before it enters triode, call that point B. That point B is Vgs minus Vt. Okay, so that's what, and this is I show this on the next slide. I actually copied it from my previous course material, last year's material, but it's attached to this problem, right? So make sure you're not surprised as to why this is the case. Sorry, why this is the case. Okay. So maximum signal at the drain is plus or minus 0.8. That means Vd equals the bias plus the signal. At minus 0.8, you can write it like this. So Vd is 0, right? The drain voltage has to be 0. So Rd then is phi by Id, which is 12.5 kilo ohms. Okay. So all that was part A. So all we did was establish the values of Rs, Rd and Rg subject to this one condition, that at the drain you cannot go more than plus or minus 0.8 volts. When the input resistance at the gate is 10 meg. Okay. So using that condition, we were able to solve and come up with Rs and Rd. That's why I put this arrow here, the two important resistance values we needed. Next we come to part B, which is just to find the value of Gm and Ro, right, which is a straightforward application of the formulas for Gm and Ro. Next we create a CS amplifier in part C. So then we use the CS formulas for overall gain, and that comes out to be minus 9.6. In part D, terminal Y is grounded, so it is a CD or a source follower. Here you use this formula to get the voltage gain, which is roughly 1 because it's a source follower. Looking into the terminal Z, we see Ro equals the parallel combination of these three, which is 4.473 ohms. Lastly, terminal X is grounded, so it becomes a common gate amplifier. Here Ig is given. So based on this, you can, and the fact that AVO is this, I signal is given, the capacitor is a short, R signal is given. Because it's given as a current, you put the resistance in parallel. Remember that. If this was a voltage, then you could put that in series. So V signal VSG at this point, which is the source to gate, is this I into R, which is this. So Vy, the output voltage, is the voltage gain times the V signal, which comes out to be 0.6 volts. So I hope this is clear for the CG amplifier. Okay, I have a few more minutes to do the last problem, which is the source follower. So you have two circuits. One of them is a source follower, another one is a common gate, CG. And he does something interesting. He takes this source follower output and connects it to the input of the common gate. Remember, this has a low output resistance, this has a low input resistance. If they are connected, then what happens to the overall voltage gain? That's what needs to be found. Okay. So pretty straightforward application, but interesting. So first you find for the source follower the open circuit voltage gain and the output resistance. Then for the common gate, you find the input resistance with for part B you find the common gate values, AVO and input resistance. Now if the CD output is connected to the CG input, then Vi2, the V input becomes this of the gain of the CD times the input voltage dropped, so that you get this formula. So then VO, which is AVO of the CG, times the Vi2, which is the input of the, is the Vi2 here. So the overall gain or the output becomes the gain of the CG stage times the input it sees, and what it sees is what we just found. So you get this VO in terms of VI and these numbers. So VO by VI, which is the overall gain, comes out to be 7.15. Okay. So with that, we have solved, or we have at least tried to solve a bunch of problems to help you with the understanding MOSFET amplifiers. Make sure you understand all these examples, all these numericals I have shown you. Please do the homework problems for the week. There also you get some more exercise on solving problems. If you do that, you should be good. Of course, make sure you read the textbook material also carefully. Okay? Thank you.